Oh, all right, so what they did is they found the components and then they put it back into polar form. As opposed to what I did, where I just defined it J hat and kept it in that form.
So you don't make these explanations?
No, it's from the book.
What in the world? Some of these don't make sense. I feel like they could be one step, like this could have easily been one step. This makes so much more sense than what this book. I don't even know what that is.
So if there are any mistakes in it, the mistakes are not mine, other than I didn't proofread it.
Yeah, because one of the questions, the one that you answered earlier, where it was like, oh, the 60 plus 30 equals 90 degrees, there was a typo that said theta 1 minus theta 2 would equal 90 degrees, and I was really confused because I was like, no, I'm doing the exact opposite. But then when they show how they got to the answer, they used the plus instead of subtraction, and I just
Yeah, technically they're this is, since it's below the axis, negative 60 degrees, so it's 30 minus negative 60. That's how they defined it.
But I guess like I understand how to get the change of velocity because I remember like the formula that they're using, but I just don't understand how they're finding theta.
So this ends up being, this was 10.5, I think, from what I remember seeing, and then this whole thing was 18 point something.
No. Yeah, 19.7.
19.7.
Yep.
Whatever the numbers happen to be. So, in terms of putting it in polar form, it's 10.5 in the I hat direction, so it's 10.5 this way. 19.7 in the J hat direction.
Isn't that rectangle form?
This is rectangular form here. To get it into polar form, which is what they did, my hypotenuse is my final speed, so Pythagorean theorem.
Oh, so it's r theta, that's polar form again?
Say it again?
R comma theta is polar form, right?
Yes.
Right.
Yes. And to find this angle here, well, I have the opposite and the adjacent sides, so theta would be the arctan of the opposite over the adjacent. Which presumably is
Isn't
what they
it
did.
22.3? That's the,
It should
oh
be
wait,
more than
not
45.
theta, I was looking at the hypotenuse.
Oh, you got 22.3?
Yeah, 22.325, blah, blah, blah. Hey, before we walk into this test, can you,
See, like I'm not understanding. Why am I getting? Oh. Sorry, Dr. Fox. This is so embarrassing. I just realized when I was putting it in the calculator, I clicked tan instead of arctan.
That would make a big difference.
So I started yelling. For no reason. Okay.
hey, before we walk into this test, can you go over the second question from yesterday's quiz? Because I really don't want to go into this test without knowing how to do that.
That was the spring.
Yeah, I have the values right here. I
Right.
happen to remember them.
Any other questions on this before I pick up the eraser and answer this other question? So that was the pogo stick problem.
Yeah, the spring constant is 3.0 times 10 to the 4. The pogo stick can compress by 15 centimeters. The total weight of the boy on the pogo stick is 35 kilograms.
That would not be the total weight. That'd be the total mass.
Sorry, total mass. Gravity is on Earth 1, Earth 1.
All right, so when the pogo stick is compressed completely, I've obviously simplified my version of a pogo stick here. Basically took out the stick and just left the spring. So it's naturally that is where the spring is if it's not fully compressed. So this distance here being 15 centimeters. And then it springs up into the air. So I'm going to assume that he starts out at height is equal to 0.
Hold on, why is the 15 centimeters above the ground of the pogo stick?
It compresses, that's how far the spring compresses. The spring is
So
like
wouldn't
this
it go-
naturally, then it gets pushed down.
So wouldn't it here, like below the stick instead? There?
All right, I think it's a misinterpretation of my drawing, so let's do that a little bit differently. Ground. Pogo stick,
Uh-huh.
boy.
Okay.
And then boy on pogo stick.
Oh, so that is already the compressed.
Yeah, that was the intent.
Oh, okay.
So that's
Let me
15
redraw that
centimeters. And how high up does he bounce? It cannot be from the ground because they didn't give us enough information. It has to be from whatever the maximum compression is. So how far up will he go? Well, at this point, he's at rest. At maximum compression, he's not moving. It's that turnaround point. At the highest point, he's also not moving, so his kinetic energy is 0 at both places. So what we're doing is we're transferring potential energy, the elastic potential energy, into kinetic energy, and then into gravitational potential energy.
Okay.
So, ideal spring, gravitational force are both conservative, energy is conserved. And so we have the energy initial equals energy final. All the energy initially is
Potential.
elastic potential, 1/2 K delta X squared initial. And that's gonna be equal to, because when he's jumped into the air, the spring is now in its natural position, presumably. It's gonna be equal to the final energy, which is all gravitational potential. It's MgH final.
I was right about, dang it.
And you're trying to find HF.
Okay,
So
so,
you're given K, you're given delta X, you're given him, and,
delta X is 15, right?
or 0.15, depends on what unit you wanna work with.
Well, that was my first problem, I didn't convert. Okay, what's the spring constant unit again? Newton per,
Newtons per
time.
meter.
Per
It's the
meter?
amount of force required to deform the spring.
But it's not times, it's divided by.
Yes, it is, correct.
Okay,
Unlike torque, which is times,
okay,
despite what some students have insisted otherwise.
okay. I'm good with that.
You know, Talon, if you were sitting right by the camera, we would pick up all of that.
Yeah, why do you think I'm sitting back here?
And that last thing wasn't picked up by the camera, the international fans are going to be wondering what noises you're making.
He's coughing.
How do you know you have international fans?
What's that?
How do you know you have international fans?
Why would I not
Ego.
have international fans?
It's ego.
I know.
This is physics.
Yeah.
A website that has prompted comments of, what the hell is this? It looks like I'm starting halfway through a lecture. How did I end up on this part of the internet?
Welcome to physics, you're stuck with us now.
To the person who asked how to end up in this part of the internet, I replied, blessed or cursed. Oh, yeah.
It was a message.
Dr. Fox, I have a quick question.
Yes.
So one of the questions says a 30,000 kilogram freight car is coasting at 0.5 meters per second with negligible friction under a hopper that dumps 110,000 kilograms of scrap metal into it. What is the final velocity of the loaded freight car, whatever?
Yep.
So, I just, is that a collision
It is, the trouble with, it's not really trouble, the thing you have to realize is that we have this vehicle traveling horizontal to the ground, and then stuff gets dumped into it this way. So officially, it's a two-dimensional problem, but we really only care about one dimension of it. I'm assuming when stuff gets dumped into the truck does not sink into the ground.
Right.
So when this stuff gets dumped in, that's vertically, it's a perfectly inelastic collision. Actually, it's perfectly inelastic either way. But so there's gonna be this impulse that is acting upwards that keeps the truck from pile driving into the ground. So the long and short of it is, in the I-hat direction, or in the horizontal direction, you have the initial mass times its initial velocity. And then afterwards, you have the initial mass of the truck
Right.
plus what you just dumped into it.
Can you tell me if this logic is sound?
Not yet. I assume you're gonna follow it up with some bit of logic.
I did it wrong, right?
Okay.
That might change things.
All right, did you follow the, okay.
I forgot to.
I was just wanting to make sure that I understood that it was still a collision problem, even though there wasn't an actual, like a second object going at a speed, so, I don't know. That's all. Sorry. I'm so excited to.
Other questions?
I agree, we should.
All right, Abigail's here, we can begin.
Abby, get back up, get back up.
Or maybe it's just not the day to harass you. My first year of teaching, a student brought his dad's convertible to the school. It was parked in the parking lot, and it started to pour down rain. And I was in a mood, and he said, "Mr. Fox, can I go to my car?" And I said, "Let me think about that." And he didn't wait for my response, because it was his dad's convertible, top down. So he runs out, comes back, and we're ready to harass him when he comes back, but he comes back and he's clearly not in the mood for anyone to say anything to him. He looks like a drowned rat.
Oh.
It really is. Anyway, you did not come in looking like a drowned rat, so it beats that situation. All right, any other questions again?